Assalamualaikum and hi to Madam Haslinda. Today, my teammates and I will present about waiting line model which is based on chapter 5 for QMT342 subject. But first of all, I would like to show you the members of this group. We have Nur Afini Fitra, which is myself, Intan Karunisa, Nur Aini Fazlin, and last, we have one Nur Zulaika Auni. In this video, we will present the introduction of Family Mart, convenience store, characteristic of selected queuing system, calculation and outcomes, and also the conclusion. First, I'm going to explain the introduction of Family Mart. What is the business type for Family Mart convenience store? It is retail convenience store chain that operates on a franchise model. Next, what are the operating hours of Family Mart convenience store? The operating hours for this store are from 6 a.m. to 12 a.m. midnight daily. Furthermore, where is the location of Family Mart convenience store? It is located at number 15 Jalan PKY1, Pusat Komersial Yayasan 85000. Lastly, what types of services are offered by Family Mart convenience store? This store provides fresh food, a selection of ready-to-eat meals such as bentos, sandwiches, and onigiri. Next, bakery freshly, baked Japanese-style bread and pastries. Cafe, freshly brewed coffee and a variety of desserts. Snack bar, hot and freshly made snacks for quick buys. Daily necessities, a range of everyday items including toiletries, household products, and more. Without wasting time, here I'm going to explain about the characteristic of queuing systems. First, we have arrival characteristic, second, waiting line characteristic, and third, service facilities characteristic. First, I'm going to explain about arrival characteristics for Family Mart convenience store. The size of calling population is unlimited. Population size which can serve all of the customers that arrive at the same time. And the pattern of arrival is customers must wait in the waiting line to make their orders. Time almost the same because it is based on the number of orders at one time. Moreover, behavior of arrival. Here we have three types of behavior of arrival. First, patient customers, which they wait in the queue until they are served and they do not switch between the lines. Second, reneging customers. They enter the queue but becomes impatient because the waiting line is too long and leave before being served. And third, bulking customers. Customers decide not to enter the queue at all upon seeing its length or anticipated waiting time. For waiting line characteristic, queue length is unlimited line and queue discipline is based on first in first out FIFO basis. Customer who arrive first obtain the service first, while the last arrival receive the last service.
Now, let's look at the service facilities characteristics for Family Marts. On the left table, we have the service system Family Mart operates with two counters. The first counter is for placing orders and making payments. The second counter is for waiting to pick up complete orders. The system is a two-phase queuing system classified as a single server multi-phase system. On the right, we see the service time details. For the pickup counters, the service rate is 34 customers per hour with an arrival rate of 21 customers per hour. For the payment counter, the service rate is 180 customers per hour, reaching the arrival rate of 180 customers per hour. We will dive into the calculation and outcome from our observation at Family Mart. This table summarizes the data collected between 8:20 p.m. and 9:20 p.m. It includes key timestamp, the arrival time in line for each customers, the arrival time at the counter after waiting in line, and the end time at the counter once their transaction or service was complete. On to the QM output for the payment counter. Here, we analyze the waiting line results. First, we have the arrival rate denoted as lambda, which is 21 customers per minute. This indicates the average number of customers arriving at the payment counter every minute. Next is the service rate denoted as mu, which is 180 customers per minute. This is the counter's efficiency in serving customers. There is only one server, meaning one payment counter available for this process. Now, let's discuss the performance metrics. Average server utilization is 0.12, which shows that the counter is utilized only 12% of the time. Average number of customers in the queue is 0.02, indicating almost no significant waiting line. Average number in the system is 0.13, meaning there are around 0.13 customers either waiting or being served at any moment. Regarding time, average time in the queue is 0.04 minutes or about 2.64 seconds. Average time in the system is 0.38 minutes or approximate 22.64 seconds, which includes both waiting and service time. Next, we have the probability table for the first phase, which is the payment counter. This table shows the probability of the number of customers in the system at any given time, denoted as K. For example, the probability that there are no customers in the system, K equals to 0 is 0.88, which is there's an 88% chance the payment counter is idle. Similarly, the probability that there is exactly one customer in the system, K equals to 1, is 0.10. The column probability number in system less than or equals to K represent the cumulative probability, which tells us the likelihood that the number of customers in the system is less than or equal to a certain value of K. For instance, for K equals to 1, the cumulative probability is 0.99, meaning there is a 99% chance there are one or fewer customers in the system. Lastly, probability number in system greater K shows the complement probabilities, representing the chance of having more than K customers. For example, for K equals to 1, the probability is 0.01, indicating a very low chance of more than one customer being in the system. Slide highlights the sensitivity analysis for the numbers of servers at the payment counter in the first phase. As we increase the number of servers, the average server utilization decrease. For example, with one server, utilization is 12%, but with 5 servers, it drops to 2%, indicating less workload per server. Similarly, the average number of customers in the queue, LQ, is negligible from 2 servers onward, meaning there are visually no waiting lines. The average number of customers in the system, L, stabilized at 0.12 regardless of the numbers of servers, showing consistent service efficiency. In terms of time, the average waiting time in the queue, WQ, and the average time in the system, W, also remain minimal, staying at 0 or 0.01 minutes across different server setups. This slide shows the waiting line result for the pickup order counter. The arrival rate denoted by lambda is 21 customers per minute, while the service rate mu is 34 customers per minute, with just one server in operations. The average server utilization is 0.62, meaning the server is busy 62% of the time. On average, there is one customer waiting in the queue, LQ, and the total number of customers in the system, L, including both those being served and those waiting. It's approximately 1.62. Now, looking at time. The average time in the queue, WQ, is about 2.85 minutes or 171.04 seconds. The total time spent in the system, which includes both waiting and service time, W, is around 4.62 minutes or 276.92 seconds. These results highlight the performance of the pickup counter, suggesting moderate efficiency but room for improvement, especially in reducing waiting times. It shows 3 columns for each value of K, which represent the number of customers in the system. The first column, probability number in system equals to K, indicates the probability of having exactly K customers. For example, there is a 38% chance of having 0 customers and a 24% chance of having exactly 1 customers in the system. The second column, probability number in system less than or equal K, shows the cumulative probability of having K or fewer customers in the system. For instance, the probability of having up to 2 customers is 76%, and for up to 3 customers it rises to 85%. Finally, the last column, probability number in system larger than K, indicates the probability of having more than K customers. For example, there is a 15% chance of having more than 3 customers in the system, and this probability decreases significantly as K increases. This slide presents the sensitivity analysis of the number of servers for the second phase, which is the pickup order counter. With one server, the average server utilization is 62%, meaning the server is busy most of the time. The queue line, LQ, averages on 1 customers, and the total number of customers in the system, L, is 1.62. The waiting time in the queue, WQ, is 0.05 minutes or around 3 seconds, while the total time in the system, W, is 0.08 minutes or around 5 seconds. As we increase the number of servers, the server utilization drops significantly. For example, with 5 servers, the utilization is just 12%. Similarly, the queue length, LQ, and waiting time, WQ, become negligible, reflecting a well-managed system with minimal delays. This analysis shows that the increase the number of servers can greatly improve efficiency and reduce waiting times, ensuring a smoother customer experience.
Okay, so let's continue with the calculation part. Okay, calculation and outcomes for payment service. Let's dive into the calculation and outcomes for our payment service system, assuming we have 1 server. Okay, first, we start with the key parameters. The arrival rate or lambda is 21 customers per hour, meaning on average 21 customers arrive every hour seeking service. Okay, the service rate mu is 180 customers per hour, which indicates the server can handle up to 180 customers per hour. Okay, so for part A, utilization factor. The utilization factor is calculated using the formula P equals to lambda over mu. Substituting the values, so P equals to 21 over 180. This gives us the probability of the system being busy, which is about 11.67%. In other words, the server is busy 11.67% of the time. Okay, so for part B, probability of the system being free. To find the probability that system is free, we use the equation P plus P naught equals to 1. Here, P naught represents the probability of the system being free. Substituting P equals to 21 over 180, it will become 21 over 180 plus P naught equals to 1. Solving for P naught, P naught equals to 1 minus 21 over 180, so P naught equals to 53 over 60. This means the system is free and ready to serve customer approximately 88.33% of the time. Okay, so for summary, the server is busy 11.67% of the time, and the system is free and available for new customers 88.33% of the time. These calculations are crucial for understanding the efficiency of our payment service system and ensuring we can handle customer demands effectively. Okay, now, so let's analyze the average number of customers in the queue and in the system for our payment service setup. Okay, so for part C, average number of customers in the queue, the formula for calculating the average number of customers in the queue is LQ equals to lambda squared over mu in bracket mu minus lambda. So by substituting the values, LQ equals to 21 squared over 180 in bracket 180 minus 21 equals to 49 over 3180, approximately 0.02. So this means on average there is approximately 0.02 customers or close to 1 customers waiting in the queue. Okay, so for part D, average number of customers in the system. To find the average number of customers in the system, we use formula L equals to lambda over mu minus lambda. Substituting the values, L equals to 21 over 180 minus 21 equals to 21 over 159 equals to 7 over 53, approximately 0.13. This indicates there are about 0.13 customers in the system on average, including both those in service and in the queue. Okay, so for summary, the average number of customers waiting in the queue is approximately 0.02. The average number of customers in the entire system is approximately 0.13. These results highlight that our system is highly efficient with minimal waiting times for very few customers in the queue or system at any given time. So this is a great indicator of the system's capability to handle the current demand effectively. Okay, now, so let's look at how much time customers spend waiting in the queue and in the service for our payment service. Okay, so E, average time a customer spends waiting in the queue. Okay, so the formula for calculating the average time a customer spends waiting in the queue is WQ equals to lambda over mu in bracket mu minus lambda. Substituting the given values, WQ equals to 21 over 180 in bracket 180 minus 21 equals to 7 over 9540, approximately 0.0007 hours. Converting this to minutes, WQ approximately 0.42 minutes. This means a customer spends on average 0.42 minutes waiting in the queue. So part F, average time a customer spends in the system. The formula for calculating the average time a customer spends in the entire system is W equals to 1 over mu minus lambda. Substituting the values, W equals to 1 over in bracket 180 minus 21 equals to 1 over 159, approximately 0.006 hours. Converting this to minutes, W approximately 0.36 minutes. So on average, a customer spends 0.636 minutes in the entire system, including both waiting and being served. So for summary, customers spends an average of 0.42 minutes waiting in the queue. The total time spent in the system, including service, is approximately 0.36 minutes. This matrix show that our payment service is extremely fast and efficient, ensuring minimal wait times for customers.
Next, to calculate the pickup service, we have service rate lambda equal to 21 customer per hour and the arrival rate mu equal to 34 customer per hour. So we can calculate for the utilization factor, which is rho equal to lambda over mu, where we get 21 over 34, which is represent for the probability of system busy. Next, to find the probability of the system to be free, the formula given is rho plus P naught equal to 1. We get the rho before, which is 21 over 34, substitute into the formula and we will get P naught equal to 13 over 34, which is the probability of the system to be free. Besides, to find the average number of customers in the queue, we can use the formula LQ equal to lambda square over mu in bracket mu minus lambda, and we substitute the value of lambda and mu into the equation. We will get the LQ equal to 441 over 442, which is, we convert into point, we get 0.99, which is almost to 1 customer. For the average number of customers in the system, we can use the formula L equal to lambda over mu minus lambda, where we substitute the value of lambda and mu into the equation. We will get L equal to 21 over 13, which is L equal to 1.62 customer. To find the average times of customers spent waiting in the queue, we can use the formula WQ equal to lambda over mu in bracket mu minus lambda, which we substitute the value of lambda and mu into the equation. We will get WQ equal to 21 over 442, which is WQ equal to 0.05 hours or 2.85 minutes. And lastly, for calculate the average times of customer spent in the time system, we can use the formula W equal to 1 over mu minus lambda, and we substitute the value of mu and lambda into the equation, and the final answer will be W equal to 1 over 13, which is 0.08 hours or 4.62 minutes.
Okay, so now let's move on to the conclusion of our discussion on waiting line models. So in operation research, the waiting line model is a structured approach that helps us understand and improve customer flow in system with limited service resources. By applying these models, businesses can make better decisions to enhance productivity, reduce wait times, and improve the overall service quality. Let's address a couple of key questions. First one, is the number of services provided adequate? Yes, it is. This is because the customer arrival rate is lower than the service rate they receive. This means our system has sufficient capacity to handle the current demand. Okay, so for the second questions, are customers happy with the waiting time? Definitely. Customers are likely to be satisfied because they don't have to wait for long for services. To summarize, if the service rate denoted as mu is greater than the arrival rate denoted as lambda, there is enough capacity to serve clients quickly and efficiently. Okay, so this insight demonstrates how the waiting line model contributes to optimizing service systems for both the business and its customers. So thank you.